Hello and welcome to another one of these ADD videos. Today we're going to be looking at a weak strong titration example. Again, recap: a titration involves a neutralization reaction in which the general scenario is acid plus base equals salt plus water. We're going to need to know the pH before it begins, during the titration, at equivalent points, and after equivalence points. So before the titration, how do we do it again? We come over here to our rice table, and the rice table over here will have an initial concentration of your acids, no ions because there's no dissociation. Remember, water is a liquid with a fixed concentration, so we don't need it in our rice table. And we do the number minus x, x and x, set up your Ka. During the titration we use Henderson-Hasselbalch, which is over here, and at equivalence point you switch over to the other species. So if you have an acid, it becomes a base, or a base becomes an acid. And we're going to look at all that through this example. So here we have 0.01 molar potassium hydroxide. It's a strong, you know what, let's use a different base. Let's use sodium hydroxide, because last time I used potassium hydroxide. And it's being titrated into 50 mils, 0.1 molar acetic acid. I'm going to abbreviate acetic acid here as HAC. This is what you'll see, or C2H3 O2H. Either way, it's a weak acid. The Ka for this acetic acid is 1.76. Most books just use 1.8 e to the negative 5. Right away, what that should tell you is we can use that approximation rule in which the change, remember over here, if you watch the concept video, is negligible because there's such little dissociation on this weak acid. So if we were to do our rice table for part A, it would be HAC, aqueous. I'm not going to write water. It's liquid, it's fixed, there's no change in concentrations. AC minus, aqueous, plus H plus aqueous. And the initial concentration here is 0.01 molar. There's nothing here, minus X, plus X, because they're on the reactant side. Product side. Here we have 0.01 minus X. We have X and X, so we have Ka equals X squared for 0.01 minus X, but remember that Ka is 1.8 times 10 to the negative 5, right? So what does that mean? That means that we can ignore this change. It's not part of it. So if you multiply both sides by 0.01, that's what we get. Turn on the calculator. 1.8 times 10 to the negative 5 times 0.01 is 1.8 times, of course. Sometimes we become a little too calculator dependent, and then square root. X would then equal 4.24 times 10 to the negative 4th. Are we done? Is that the answer we were looking for? No, that's just the proton concentration. So when you do negative log of answer, you get the pH of 3.37. There's before the titration begins, part A. Now, after 10 milliliters of KOH, so during the titration we have to use Henderson-Hasselbalch, so pH equals pKa plus log of A minus or HA. Now, you could do moles, but remember, or molarity, but remember I prefer moles because the volumes are the same, so we'll just do N's. Little n of A, N of beaker. Alright, so pKa, if you do the negative log, you're going to get 4.76. plus log of, see how much did we add, 10 mils times 0.01, so that's 1 e to the negative 4, or 0.1 e, or millimolar, or millimole, sorry. That's what we added. And then if we subtract, we're going to get 0.4 millimole. So we have 0.1 divided by 0.4 log answer plus 4.76 is 4.15. This was a negative 0.6 something or other. When you do it all, you end up with 4.1, actually 6 if you round up. So that would be part B. Alright? So what did I do here again? I found the moles of the titrant added. If you remember, the moles of the titrant is the ionized base, and that is what's going to neutralize your acid that you had in your beaker, which then produces your A minus. Okay. Alrighty. Next question says, what volume would we need to get pH equal to pKa? Alright, so that's halfway to the equivalence point. I'm going to do that one up here. Let's zoom in so I can get a little bit more space out of the whole picture. So for pH to equal pKa, oops, let's make a marker there. Sorry about that. That's halfway at equivalence point. And that only occurs when this is a log of 1. That means that the moles of the titrant added has to equal the moles of the beaker left. So if you just take the moles that were in the beaker, which was 0.5 millimoles, and cut them in half, it gives you 0.25 millimoles, and that's the number of moles at halfway to equivalence. Then what you can do is you can say, well, I know the molarity of that acid is that, and I know the moles now is 0.25 millimoles, and I'm looking for the volume to achieve that millimoles. Okay, so what we do is we just multiply the VT on this side and divide 0.25 times 10 to the negative 3 moles over 0.01 molar. So when you do that, you get 0.025. I'm trying to get back to the problem. 50. Okay. 0.25. I'm just double checking my calculation, make sure I don't make any silly mistakes. Ooh. I think I cut a mistake. Let's see. No, that's right. Okay. Everything looks like it's okay. So that would be the volume in liters, right? Because this was in moles, or molarity, which is moles over liters. So if we wanted milliliters, we'd multiply by 1,000. It'd be 25 milliliters, which is half of the volume of acid we had in the beaker. Alrighty, so that, oh, by the way, it just occurred because they were equimolar. The concentrations of the acid and the base were the same molarity. So drop for drop, mole for mole, we were neutralizing. Alright, that takes, oh no, at equivalence point is left, right? So final answer for that one was 25. At equivalence point. So what happens at equivalence point is you got to realize is we've completely neutralized the HAC. Now all we have is its conjugate left, the acetate ion. That would be CH3O. Oops, forgot the other C. C2H3O. How do you want to do it? My eraser doesn't want to work. C2H3O2, we'll say like that, minus. So what is the difference here? Well, now because we have a base over here, we're going to get the conjugate acid and create the hydroxyl ion at equivalence point. So instead of Ka like we did before, we have to do Kb calculation. And we have to now calculate what this new molar concentration for the AC minus is. So how do we go about doing that? Well, you have to realize that where this originated from. Where did we get these AC minus ions? Well, they came from the beaker, from the acetic acid, right, that we had in here. So the moles of your acetic acid also will be the same as your moles for your acetate ion. Okay? So in other words, we have 0.5 millimoles of the acetate ion if all of the acetic acid is neutralized. Now the problem is we don't have the same volume because we had 50 milliliters in the beaker, and we're going to need to add another, oops, let's make it in liters, sorry. That was sloppy, just like my eraser. Okay, 0.05 liters. Plus, if you remember, we just did halfway to equivalence point was 25 milliliters, so the other half would be another 25 milliliters, so that's 50 milliliters. Again, they're same molarity, that's why this is occurring. Different molar ones will get different volumes to get to the equivalence point. So here we have 0.1 liters, so that would be 5 millimoles for the initial concentration. Nothing here, nothing here, so it's still initial, big initial right there. And then the change would be minus x here, and x there, and x there. So we have 5 EE negative 3 minus x, 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 x squared equals 5, or over 5e to negative 3 minus x. Now this is going to be equal to your Kb. Well, we don't know Kb, but remember that Kw over Ka can give me my Kb. And Kw is 1 times 10 to the negative 14. Divided by that 1.8 times 10 to the negative 5 gives you the Kb, which is 5.5 times 10 to the negative 10. I'm going to do 5.56 times 10 to the negative 10. Again, that value allows you to negate this change in the x in the denominator. If you didn't do that, you'd be stuck in quadratic formula land, and most of you guys fear algebra like Superman fears kryptonite. So go through and try to take as many shortcuts as you can, and again, practice. That's the key that unlocks many doors. Alright, so if you multiply that across, you get, do it with me, don't just sit there and listen and watch. and square root that answer. You get 1.67 times 10 to the negative 6. Again, this is your oh no, actually this is at equivalence point, right? So this is your hydroxyl ion concentration. So when we do negative log of that, we get POH equals, let's see, negative log answer 5.77. Are we done? No, because we wanted, or actually 5.78 POH, so we're going to have to do 14, 8.22, which kind of makes sense. We're now more on the neutral scale. So then pH would equal 8.22. So any other subsequent addition is going to be using KB calculations, okay? So that's basically it in a nutshell. This is not much of an ADD video because it's already 16 minutes long, but this is a tricky concept. I want to make sure and take my time and do several aspects of this problem, okay? So the main thing to remember before the titration and at equivalence point, we're going to do Rice tables, but during the titration, where we're actually doing neutralization reactions, we do good old Henderson-Hasselbalch equation right there, okay? So I hope this has clarified things a lot. Make sure you practice. The more you do these things, the more they become second nature. And check out the rest of the example videos. Thank you, and have a nice day.